This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. When we say our future in the solar system is to become an interplanetary species, folks tend to think of a handful of planets, but as we'll see today, our destiny awaits us on a million smaller worlds too. So today we are continuing our look at becoming an interplanetary species. This is part 5 of our series, loosely following the National Space Society's Roadmap to Space Settlement as our guide, and I've linked the complete document in the episode description. Last time we looked at establishing our first colony on another planet, Mars, and today we'll cover the roadmap's milestones 26, 27, and 28, settling asteroids and moons, as well as orbital habitats of our own creation. Now back in part 2 we looked at colonizing the orbital volume around Earth, and we talked about the importance of the moon as a source of raw materials. An important point we made there was that because the moon's lower gravity, only a sixth of Earth's, and the fuel cost of lifting materials out of a gravity well, it's actually much cheaper to move raw materials from the moon's surface to the construction yards in low Earth orbit than it would be to lift them up from Earth's surface only a few hundred kilometers away. However, even though the asteroid belt is even farther away, hundreds of millions of kilometers, in many cases it will be even easier to bring resources to Earth from there than from the moon. More to the point, it is a great place to get resources for other efforts in the solar system. So too, our moon is but one of many in the solar system, and all of them are easier to get resources off of than their planets. So we'll be looking at how to do this, why we want to do this, and how a basic solar economy will develop from it to fuel colonization of this solar system, and to set the stage for reaching and colonizing the next. Milestone 26 is the robotic characterization of asteroids, particularly the near-Earth asteroids, those whose orbits make them the cheapest to bring materials back from. These asteroids happen to also be the ones that are the greatest potential threats to us. Telescopes and radar arrays in Earth orbit will be able to tell us a lot about asteroids, but probes like NASA's OSIRIS-REx probe will let us take direct samples and place beacons on these objects to make it easier to track and monitor them, and see which ones have the resources we want. In the long term, we will want them all, and there are millions of asteroids in our solar system. Each one may represent billions or even trillions of dollars of valuable resources, so the ability to catalog these with cheap robot probes will be invaluable, and one of the earliest manufactured goods we might expect to be built in space for use in space is likely to be those probes. This will be a continuing project of course, but early on we want to focus on those near-Earth asteroids and on finding any with metal concentrations. Some of them may be easier and cheaper to get metal off of than the moon, and for that matter, while we often picture our orbital habitats as big spinning cylinders, this is likely to only be the internal view. Wrapping those cylinders in a shell of cheap material, like rock from these asteroids, represents a great shield against meteor damage and to minimize leakage of air. Milestone 27, the utilization of asteroids, is therefore not just about mining them for gold or other precious metals, but also their use in Milestone 28, construction of orbital space settlements and other space habitats, where they will provide not only the metal for the structural elements, but also the bulk exterior shielding and the interior landscaping, all the dirt, air, and water we'll need. And though we call the parts of this roadmap milestones, they will be ongoing overlapping processes we'd expect to see under constant upgrade and expansion. In the early days of asteroid mining, the focus is entirely on finding asteroids with the least delta V relative to Earth, then finding the ones with gold and platinum on them, but eventually becomes about finding the very tiny ones because you want every drop of raw material in those asteroids, and every one of the smaller ones represents something of a navigational hazard. In a similar vein, early orbital settlements will be about what is cheap, but then again, so will later orbital settlements. What changes is what is cheap. As you get that asteroid utilization going, resource scarcity shift. Sometimes it is suggested we might bring an asteroid back to Earth to place in orbit. Now, this is sometimes viewed as a bad idea because it might land on us, but that's not really a concern. You would need to be careful to have redundancies and security on board when pushing the asteroid in, but you don't exactly accidentally hit a planet, so that's a safeguard against intentional sabotage. Once it's in orbit, it's less of a concern. There's two reasons why you wouldn't bring whole asteroids to Earth orbit, and the first is that asteroids are often just big balls of loose gravel, a great recipe for adding more dangerous space debris to Earth's orbit. That's easily rectified by covering the asteroid in some shell of plastic or foil. The other big concern is the sheer amount of mass. If an asteroid is found to have a gold or platinum abundance of 1 part per thousand, then we only want to ship home that 1 part per thousand, not blow 1,000 times more fuel bringing the whole thing home. Now as time goes by, you're interested in more and more of the materials in those asteroids, though often for local use as we colonize the asteroid belt. However, while we don't want to move asteroids, early on there is some motivation to bring small asteroids right back to Earth orbit, as ones a few hundred meters across might be nudged from their near-Earth orbits into stable orbits in cislunar space, and converted into orbital settlements with a lot of mass and shielding available. This way was often contemplated by the L5 Society, the precursor organization to the National Space Society, as a way of sourcing the mass for large Lagrange point orbital settlements. Alternatively, last time in the series we were discussing Aldrin cyclocastles between Earth and Mars, essentially large space stations on elliptical orbits that take them by both planets, and a lot of near-Earth asteroids might be ideal for conversion to cyclors between Earth and other destinations in the solar system. As we mentioned earlier in the series, we would always anticipate the majority of space habitats as Earth orbital settlements until such time as cislunar space was truly crowded to capacity, but let us ask what other places we might have them. A big factor in that, of course, is how well humans can handle lower gravity. If the answer is that even Mars has too low of gravity for humans to comfortably live in, then humanity's future in space will principally be in spin gravity stations from the outset. If we can handle lower gravity like our moon and other large moons of our solar system have, then we are likely to grow initially on those places and only begin heavy construction of spin gravity stations like the O'Neill cylinder when we have more people than Earth and all those other places could handle, even if they were all converted into ecumenopolises, planet-wide cities, or in this case, moon-wide cities. Even then, we'd expect a lot of these stations around Earth, in the asteroid belt, and probably as the cyclocastles too. While the cyclors on their long elliptical orbits are hardly fast means of transport, they are ultra-low energy approaches to it, and big space stations serving in this role, complete with heavy shielding and life support options like hydroponics and gardens, are likely to become heavily used in the middle days of solar settlement. An asteroid you've hollowed out and shoved onto a cyclo trajectory between two large bodies of interest is potentially an ideal approach for this. When we say we want to hollow one out, we generally mean more like expand it like a balloon. A rocky asteroid with a diameter of 100 meters and a density of about 2 tons per cubic meter is going to mass about a megaton, or 10 aircraft carriers, and if you ground it up and made a hollow sphere out of the rock half a meter thick, your 100 meter wide asteroid is now a hollow spherical shell 560 meters wide instead, encompassing around 90 million cubic meters, 100,000 times what our space station's volume is, and which has nothing like half a meter of metal or rock as a protective skin against impact and leakage. There are several thousand asteroids in this size category that qualify as near-Earth objects alone. There are many millions of asteroids that size in the actual asteroid belt. And I want to emphasize that difference real quick, as when we're talking about asteroid mining and asteroid utilization, the emphasis is mostly on the relative handful of them that are near Earth, which again is many thousands, not the millions in the main asteroid belt. That all comes later. I would not be too surprised if virtually every near-Earth asteroid starts out converted into a cislunar orbital settlement or a cyclocastle. They represent a minimal danger to Earth if brought into orbit, as an asteroid of this more modest size on a known and decently stable orbit is easily exploded without even resorting to atomic weapons. However, they would be a heck of a hazard to other things in orbit if you did that, so assume any asteroid brought back to Earth to serve as an orbital settlement would at least be having a coating of foil or ice, or similar, applied to minimize them kicking out debris from minor impacts. Many asteroids are basically just big balls of gravel loosely stuck together, and same as you don't want to be right behind a car driving down a dirt or gravel road spraying you with everything they kicked up, you don't want any object in orbit of Earth that are producing any more space debris than can be avoided. What about actually colonizing the asteroid belt? Well, first we have to ask which belt we mean. The asteroid belt between Mars and Jupiter is actually multiple hazy belts, loosely defined as the inner, middle, and outer belt. We also have the Jovian Trojan moons and the vastly larger Kuiper belt out beyond Neptune. On top of all of that, same as Earth has thousands of near-Earth asteroids that aren't part of the belt, there are many thousands of large rocks in our solar system that don't fall into the normal collection of belts, Trojans, moons, or rings. This is a big part of space settlement and becoming an interplanetary species, because it's realizing that there are not 8 planets in our solar system, nor even a few dozen when we throw in dwarf planets like Pluto or Ceres, or the larger moons like ours or Titan and Ganymede. It's realizing that there are millions of minor planets in this solar system. Colonizing these is what's going to turn us into an interplanetary species, not setting up a handful of dome habitats on Mars or floating cities on Venus. Of those millions of minor planets, each one has the potential to be turned into a space habitat the size of the Kaplana 1 space settlement, and around perhaps 1 million into full-blown O'Neill cylinders home to 1 million people each. That's without even tapping into the dwarf planets or the larger moons, each one of which has more raw material than all the asteroids combined. This then is our true future as an interplanetary species, because those millions of minor planets aren't that minor, and what might begin as a small outpost for asteroid miners on most will likely transform over time into millions of city-states. Each one will develop uniquely, but let's consider a few scenarios. We contemplated the future of the biggest asteroids series in our episode Colonizing series, and how it might become a trade hub and agricultural center for the asteroid belt. Let's look at another case. Imagine a gold-rich and larger asteroid, such as we believe 16 Psyche to be. It's roughly 16th place in terms of size in the asteroid belt and is an M-type asteroid, meaning metallic, that we think may have been the remnant exposed iron core of a protoplanet. Our early solar system was a very different place with many more mid-sized planets, some merging together, others being gravitationally ejected from the solar system or swallowed by the sun, and many remaining as moons or failed planets like Psyche. It's also one of our earliest finds, being discovered in 1851, just a few years after Neptune and long before Pluto. Its symbol is meant to be a butterfly wing and a star, as Psyche was the Greek goddess of the soul, and that was typically represented by the butterfly's wing. Back then, we were still giving each new asteroid discovered its own symbol like all the planets had, in part because we were still calling these asteroids planets, all of them being larger examples of their type. We didn't even know there was an asteroid belt yet, but we started discovering a ton more of them about this time and were running out of symbols, so astronomer J.F. Encke suggested we just use a circle with a number in it, in this case a 16, and within a decade we discovered around 100 more asteroids, and any thought of naming each went out the window. Psyche is of interest because of its exposed metal, and we've been talking about missions there for some years now. Many of you might remember articles in recent years talking about an asteroid having trillions or quadrillions of dollars in gold in it, and those were generally referring to Psyche. Early in 2020, NASA awarded SpaceX a $100 million contract to launch a satellite to orbit and probe Psyche, and the current launch date is planned for 2022, with a Martian gravity assist to arrive in 2026. It seems probable that the first exploration of almost all bodies will be done by robots, so I've often wondered if folks living on those bodies in the future will commemorate that as a holiday. It would seem like the big three most would have would be the day the body was discovered by telescope, the day it got its first orbital probe or rover, and the day a human first stepped on it. Of course, resource harvesting might be entirely automated, especially on smaller rocks where we might just envelop them in a mylar bag and cook the materials out. But Psyche is a good deal bigger and basically is the queen of metallic asteroids. With a surface gravity of just 1.5% of Earth normal, which is quite high for an asteroid, there's still a recognizable up and down, and with an escape velocity of 100 meters per second or 400 miles per hour, you don't have to worry about accidentally kicking yourself into space from its surface or random mining debris drifting away, so you don't need to bag or dome the spots you're working on. We believe its surface to be composed of about 90% metal and 10% silicate rock, and most of that metal is iron and nickel, same as our own planetary core. That's great building material for space settlements, but the real initial interest is in its precious metals. Earth has a lot of precious metals, but most of them all sunk into our planetary core, which is why Psyche, suspected of being an exposed core of an early protoplanet, is of particular interest. That iron though is over 1 million times what we produce a year, and the long term is probably its greatest value. In the short term, there's gold in them there hills, and platinum and so on, and we estimate the total amount of metals in it, sold at modern value, would be several hundred quintillion dollars, more than 1 million times our annual planetary economy. You don't mine that all at once, and again it's the size of a medium-sized nation or state, so you don't tow that home either. You sit up on it and slowly extract raw materials at the rate the market desires. You'll be producing a lot of other metals as they're extracting the precious metals, and those you will use locally or ship off to wherever the market is willing to pay the bill for shipping them. As you'd most likely be producing large numbers of tunnels, which are very easily shored up when the gravity is 1.5% Earth normal, you can start building habitats inside those tunnels, much like the lava tube colonization we often contemplate for the moon. At roughly thrice the distance from the sun Earth is, it still gets enough sunlight that domes on the surface, or with light reflected down via mirrors, could profitably grow food. You would never have decent gravity on the place, though we'll discuss some options in the next episode for dealing with that, like using artificial black holes. So if folks want to live there, they would need to use spin gravity habitats buried in those settlements, and we discussed that more in Colonizing series too. Alternatively, you might build orbital settlements around it, using all that iron and some of that silicate for making them. We don't normally think of building space stations in orbit of asteroids, since they already have such low gravity and no atmosphere it seems a bit pointless, in favor of embedding them down to the asteroid where they'd be protected from meteors. However, this might not be too uncommon. Landing on a planet or taking off from one is always a bit of a pain, and a space station orbiting one would only have a very small delta V. Indeed, many smaller asteroids are spinning nearly as fast as their gravity can hold material on the ground, so your equatorial orbital speed relative to the ground won't be terribly high. Psyche is big enough we might consider building it with a mass driver track of its own, but it's also low enough gravity you could erect some monstrously tall space towers on it too. That's a potentially interesting scenario because inside the asteroid belt there are so many smaller asteroids whose delta V to each other or Psyche would be small enough we might just give them a shove into orbit of Psyche, if it had developed enough to have sophisticated refining and manufacturing going on. So come for the gold, stay for the industrial titan the place is likely to become. And indeed it might get fairly common to lasso smaller asteroids into orbit around the bigger ones, and flat out tether them to each other for easy transport. That's ready-made to eventually end up as a rather large nation-state of millions or even billions. Psyche alone has enough mass to forge 1 million full-sized O'Neill cylinders. I suspect that will be the path for a lot of asteroids though, especially the more modestly sized ones only a few kilometers across. A robot probe finds some nice deposits of valuable metals, folks go down and mine it for a few decades, and as the wealth pours in they expand their facilities and form a community. Even after valuable metals are exhausted, the remaining metals would be valuable to that settlement, which is capable of mostly self-sustained growth at that point, and they diversify production to engage in trade with neighbors and with Earth, which will be growing a massive cloud of orbital settlements by now. Let's consider one other pathway for asteroid utilization. Many of those near-Earth asteroids are only near occasionally. They have wide elliptical orbits that take them near us occasionally and have lower delta V to reach them than most belt objects. Many of these are ideal for early asteroid mining, and we are likely to send that material back to Earth orbit by some means like an electromagnetic catapult, solar or nuclear powered. When you are hurling mass from something in space, you move that object too, and careful timing could let you nudge that asteroid over time into a cyclar orbit between Earth and some other spots in the asteroid belt, or other planets and points of interest. Having gotten materials out of them and gotten them fairly settled, we could convert them into mobile waypoints as cyclar castles, and this might become a preferred means of cheap travel as they'd essentially be cyclar castles of the space habitat scale. Back at Earth, whose orbit is swelling with orbital settlements fueled by all the solar system resource extraction, we might begin seeing thousands or even millions of cyclar castles of various sizes and pathways emerging as having Earth at one end of that cycle. And if you saw a recent episode on interstellar trade, where we discussed interstellar cyclars, we could employ some of those same methods to make for fast-moving cyclars and space highways. Indeed, you might set up laser pushing stations on dozens or hundreds of massive cyclar castles on the same path to serve as the relay chain for fast-moving spaceships pushed along by them. This is the true path of interstellar colonization though, orbital space around Earth growing heavy with installations in a giant cloud, even as the larger moons, asteroids, and planets become slow-growing replicas of that Earth cloud, and the asteroid belts and other minor planet swarms grew from mines to hollowed-out giant habitats by the million. This might be accompanied with vast, thin, but enormous solar collectors closer into the sun, beaming energy out to places that needed it. This is interplanetary humanity, scattered across 1 million worlds without having yet ventured out of the solar system, not our usual image of a handful of terraformed planets and moons. That may happen too though, especially as practice for colonizing other solar systems, and we'll explore terraforming, para-terraforming, and our steps out into the galaxy beyond next time. For now though, just remember this. We do not need to colonize the galaxy to colonize 1 million worlds, we just have to colonize our backyard. This solar system is an immense place with immense resources, able to take us forward into being a civilization whose scope and scale rivals any of the galactic empires we see in fiction. So today we saw how asteroid mining would help shape interplanetary settlement and trade, and last week we were talking about interstellar trade. but we also look to trade with alien civilizations in our Coexistence with Aliens series, exclusively available over on our streaming service Nebula. We also show all of our new episodes there a couple days early and without ads. If you like to catch SFIA episodes early and without ads and help support the show while you're doing it, you can sign up for Nebula today and see that exclusive Coexistence with Aliens series, along with other great content from our sibling shows. However, we also have a deal running with CuriosityStream, where if you sign up for them at the link in the episode description, you not only get a 26% discount, but free access to Nebula while you're a CuriosityStream subscriber. CuriosityStream has excellent educational content of their own, and they are running a 26% discount if you use the link in the description. That's a great deal since it means you get a year of both CuriosityStream and Nebula for less than $15, and help support this show and a lot of other educational content, which is what CuriosityStream and Nebula are all about. And again, you can get a year of both for less than $15 by using a link in the episode's description. We've been discussing colonizing space, huge colonies on asteroids, moons, and planets, and our destiny as an interplanetary species, but mostly we haven't looked at the life of the individual involved in colonizing space, so next week we'll be taking a look at life as a space colonist. That's a future we might live to see, and certainly the next century promises to be quite interesting, with many challenges too, and in 2 weeks we'll ask what it will take to survive the next century so we can see that bright new future on other worlds. Then we'll close November out with our monthly livestream Q&A. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website, isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums, where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. Until next time, thanks for watching, and have a great week.